Uh, Good afternoon, everyone. Let me introduce myself for those who are newcomers for the today's session. So I'm Mithun Krishna. I'm a PhD student at IIT Bombay. So I'm taking this, I'll be serving as a TA for this course, Advanced Advanced Quantum Mechanics with Applications, and I'll try to basically complement the course by doing some theory around what's happening in the course, and maybe also do some problems. And I'll try to make sure that each of the sessions are self-contained. So even if you miss one session, it's okay. Like the next session won't refer to what happened in the previous session. It will be independent. So you can join. Like if you have any questions, feel free to join any session, even if you have missed the previous ones, and ask them. So do you guys have any questions from like the last couple of weeks? The sessions from what's already on NPTEL? If there's that, we could start with answering those questions and then have a discussion about those and then move on to what I've prepared for today. So I'll basically be talking about density matrix mostly, and if I have time, I'll also do some. Um, there were some questions and confusion about representation of states in position and momentum basis. So I'll touch upon that if we have. I think we'll be able to do it. Yeah. Okay. So is there any particular question that you would like me to start with, or can I go to the session, like the things that
Sir,
I've prepared?
actually, I have a doubt
Yeah.
in uh, in week one's video lecture number 4.
Okay. What is
So,
the doubt?
where sir was explaining the mixed state. So,
Yes.
I have a doubt in one expression he has written. How he has written, I don't know. So,
Okay. So tell me what that expression is. I don't recall.
uh, it
Do
is
you recall?
the probability of finding a system in state 5J. So, if you can open the video and then only
Okay.
it will be possible. Yeah. I can tell
Uh,
you the time stamp of it.
okay. Video means I'll have to go to NPTEL, no?
Yes, yes.
Where is it?
Sir, it is lecture number 4, week 1, lecture number 4.
Okay. The thing is, my internet is a bit slow today because Wi-Fi here is not working. So I think this might take a time. So could you tell me what the expression is so that I can write on my iPad and then discuss?
So it is the probability of finding the system in state 5J. First, he has explained the mixed state is what is mixed state. So he has
Hmm.
defined the mixed state
Okay.
density operator for the mixed state.
Okay. So I'll be doing those in the session. So let's see if it clears while we go through. If it doesn't, you
Oh,
can ask the question again and we can discuss. Is that okay?
yeah, yeah, fine.
Okay. So fine. So let me begin. So we usually in quantum mechanics 1, quantum mechanics 2 deal with uh, wave functions, right? State vectors in a Hilbert space. And we talk about Schrodinger equation for time evolution. And then say if you do measurements, state collapses. We have done all this using state vectors or wave functions. So density matrix is another way of representing a quantum state, which also, I mean, there are certain scenarios in which you cannot represent your state using a wave function, and you have to do it using a density matrix. Okay, so I'll just motivate uh, why we need density matrix from a point of view of mid state, like why we need mid state, and like density matrix is an efficient way of representing a mid state basically. So that's where the idea comes from. There's also another motivation which is basically coming from the idea about open quantum systems. So if I have a quantum system interacting with some other quantum system, and I don't want to talk about the full system. Let's say, okay, let me just uh, give me a second. Yeah, Okay. So this is the open quantum system reason for why we need density matrix. So let's have a state, two systems, A and B, right? They're closed. Yeah, closed system. So A, B combined is closed. But if I look at A is interacting with B, right? So the even though A, B together evolves using the Schrodinger equation, if you look at A alone, like the full state of this system is some psi A B. But if I if I don't have any access to one part of the system, let's say B, I can only access A. I can only do in my experiments on A. Then what happens is I cannot describe the state of A using a wave function. So this is one scenario. Like how do you describe state of A, right? So there are some scenarios in which uh, we won't be able to do that. Let me give you an example. So let's say I have two spins, okay? So or two qubits, let's say, right? So my state of the joint state psi is 0, 0 plus 1, 1 divided by root 2. So this is the no. Before that, let's just take this state. Psi is 0, 0, or more precisely 0 tensor 0. Is everyone comfortable with these notations? If you don't follow, let me know so that I can explain what this means. So what this means is there are two spins A and B, A, B, right? So what this means is A is in state 0 and B is in state 0. Then the joined uh, system, the full system A and B combined, can be represented by psi AB, which is this form. So here we know definitely that A is in 0 and B is in 1. Then we can write this. But there could be scenarios, I mean, in which let me take of this form 0, 0 plus 1, 1 divided by root 2. So what happens in this case is I cannot definitely say if my first A part is in 0 or 1, right? It's in some combination of 0 and 1, the first part. Even the second part is in some combination of 0, 0 and 1. So I cannot exactly say my A subsystem is in 0 or 1. It's in some weird combination. This is called entangled states. So in those scenarios, I cannot. So here I can write, we wrote that the states of A and B in this form as 0 and 1. But in this case, writing psi A and psi B is not possible. Okay, so this is one place where we have to deal with density matrices. So so since the course does not deal much with open quantum systems, I won't be discussing this approach to density matrices, but I'll take uh, a digression and then do it from a from the mid state perspective. Like why from a if you have a classical statistical mixture, how would you talk about mid states? So I suppose that you're all familiar with the idea about um, Stern-Gerlach experiment. So the big idea is that uh, there's an oven, right? So there's an oven in which I've heated up silver atoms. There are several silver atoms there. So it's at like very high temperature. So these silver atoms are ionized and they come out. So there's a small hole in the oven so that they come out uh, in streams of particles, right? And so the special property of the silver atom is that Ag plus ion has an extra spin. So it's not the spin, all the spins does not cancel. This says the nucleus actually has one, not nucleus, the orbitals, if I look at, yeah, can we say A is, no, we cannot. I'll maybe discuss that in next lecture because open system perspective of looking at this is also important. So we'll deal with, and I think The third week and fourth week talks about orthogonal systems, like quantum information perspective, where you define entropy, relative entropy, and things like that. So it might be better to kind of do that there. Okay. Yeah. Go ahead, Shivani. Do you have a question? Okay. So what happens in thermal life is, so we have an oven from which there are silver atoms coming. So these silver atoms have one spin degree of freedom. So they come, this silver atom can either be have a one extra spin degree of freedom, which could be oriented in any way. Right? Now what I do is I let this stream of silver pass through an inhomogeneous magnetic field. So I apply north pole, south pole. So there are like a magnet. I pass through middle of a magnetic setup. So we know if I have an electric field, let's say a positive, right, negative, and if I send some charged particle, I know that a negative particle would move this way and positive particle would move this way. They'll be deflected from their path because the electric field would basically disrupt the, like, would interact with the charge of the particle and then create a force on it. Likewise, if I have a magnetic field, spin of the particle would interact with the magnetic field, and this would lead to, you know, so depending on if what the spin of the particle is, they would deflect in different directions. So if it was a classical particle, in which case the spin is continuous variable, I'll basically get a, like, if I, so this particle basically go and hit a sheet of uh, photoluminescent material, and they make scintillations from which I can see where the particle has hit. So we expect something like this, in which from there's a region in which the spin, on average we expect the spin to be zero because it's a thermal state. So we expect a distribution of spin and values, and hence on the cardboard sheet, like on the photoluminescent sheet, we expect a, a continuous value of spin to be registered. But instead, what experiments show is we only get two spots. So what that means is that we only have two spins available. So if the particle has there are only two values of spin available, up and down, let's say. So if the particle is in, or let's say, yeah, up and down. So if the particle is in has up configuration of spin, it'll move upward because the magnetic field is pushing it upward, and then you get this spot. If the magnetic field, like if the spin is pointing downward, the magnetic field would deflect it the other way around, and then you get another spot here, right? It's easy to think if I had a like this, like we are mostly used to electric field. So if I have plus and minus coming in, charges coming in, right? So the negative would go this way, positive would go this way, and if I make a sheet, basically this will be positive and negative. So this is a spin analog of the same experiment. Okay, but if yeah, so this is when I apply magnetic field on z direction, right? So what do I mean by, how do we represent this experiment mathematically? That's the first question. So spin of the silver atom is the total spin of the silver atom effectively is just half, which means the total angular momentum. So silver has total angular momentum half. I mean, it's actually root of half into half plus one. It's cut times that, but it's a spin half particle. So this is the total angular momentum. But if I look at the z component of the, so when I do this, if I, let's say I'm applying the field along z direction, the magnetic field is along z direction. So the z component of the spin is interacting with the magnetic field. And since we only have two states, this whole system, I should be able to represent this whole system as a two-level system. So that's the whole idea about that we are going to. So let me represent this state which goes up as zero, no, as one, and this state that goes down as zero, right? So by doing this association, I can describe. So since these are spins, I can associate this so there are angular momentum. Spin has angular momentums, right? So I can associate like the Pauli matrices. No, how do I describe the angular momentum of the system? So these are described by what are called Pauli matrices. So the angular momentum along the z direction is given by the Pauli Z matrix, which has this form here. And so when I do measurement, so when I'm passing this particle through this inhomogeneous magnetic field, what I'm doing is I'm measuring what the spin of the particle is. And depending on whether it's up or down, I get these spots here, right? So so the state that I get after this whole measurement is basically zero. If I have a particle which comes here, that means my state is zero. If I have a particle that comes here, that means my state is one. That's how I'm representing that. And I can construct this matrix Z, which will describe the the spin of the particle, right? So wait. So when I'm sending some particle through this magnetic field, what I'm doing is I'm doing a measurement in the Z direction, and what this does is it in some sense give two outcomes. Either it will show that it's the spin is up, or it will tell me that spin is down, right? If it says the spin is up, that means the measure the eigen. So yeah, so I send the state psi, I get two outcomes, right? I can either get up or I can zero, or either I can get down. And this happens with some probability depending on how many of them were like. So since it's thermal ensemble, it will happen at some randomly. So there'll be some probability associated with how many zero and one I get. So the interesting part of Stern-Gerlach is that if I North Pole, South Pole, so if I send them, if I get this to be in upstate, so some of them will go up, some of them will go down, right? So this is zero, this is one. Now if I apply magnetic field again, right, all the up particles, so now these are in definite states. So they're in, the ones that went up are in zero state, and those which went down are in down state. So what this means is if I again apply magnetic field along the same z direction, this particle would again go up. Okay, it doesn't matter if I apply z field again, it'll again go up because they are now in up state. The spin of the particle is now up for this beam on the this top beam. Likewise, if I apply magnetic field, if I take the particle coming from the lower beam and apply the magnetic field along the z direction, so this is all along z direction. What we'll see is they'll keep on going down because so the particle is now in the state is has a specific state in the z direction, so either pointing up or down, and depending on which direction it's pointing, it'll go up or down. Now what happens? Now it gets interesting if I do measurement not in the z direction but in either in x or y direction. Okay, let's look at that scenario. So this is z and z. So now if I look at, so I do first a measurement in z direction. So there'll be beams going up and beams going down. So this is zero state. This is one state. Now instead of z direction, I apply some magnetic field along x direction. Okay, so there's magnetic field in the x coordinate direction. So what I see is what people like Stern and Gerlach observed in 1930s, around 1930s, is that instead of, so what do you expect when I do this? Can someone tell me what you expect if I send this one particle through a magnetic field which is pointed along x direction? You know the magnetic field is acting force in that direction. So will it go? Where will it go? Does someone have any
It
guess?
won't go.
It won't.
It won't go.
It won't go. You're saying it'll just go straight through the thing. Is that what you're saying?
No, it won't go to that because it can't be polarized on north or south.
I didn't understand. It won't go. So my question is, yeah, sure, sure. I'll repeat the question again. So initially, what we did is we applied magnetic field along z direction, right? And we got 0 or 1. And if we apply like if I take any of these beams and apply magnetic field again on the z direction, what I'll see is the beam that went up will keep on going up because the magnetic field is along the interaction. So what this mean? What that means is this pin was an up state. So this pin was an up state. So when I apply magnetic field again, since it's again an up state, it just goes up. Now my question is, if I first apply a magnetic field uh, along x direction, it will split into two ways. Okay, and then if I, yeah, okay, if I apply now field along north south, but along x direction. So initially the field was applied. So here the field was applied vertically, but here the field is applied horizontally. Okay, so there are some comments in the chat. Let me. It won't go up, but it will go straight. Okay, you're saying it won't go up. I agree because the magnetic field is now along x direction. So if it was a classical particle, it may not deflect because now the spin is pointing upwards. There's no magnetic field, there's no spin along x direction. So you expect it to go straight because the up spin cannot, like the spin pointing in z direction cannot interact with the x side. But since this is a quantum particle, what you see is what Anirban has been saying. There's 50% probability of getting either one, right? So there'll be some particle which will go this way, some particle which go this way. So this is pointed that way, and this is pointed this way. So this is called plus state. Let me just write that notation. And this is minus state. So what happens is now when I apply measure along the x direction, since x and z operators does not commute, the measurements are not compatible. So what happens is for as far as this x measurement is concerned, it doesn't know what, like, so the spin is now pointing along z direction. So x doesn't know what the spin is because x cannot access that degree of freedom because they don't commute. So what x does is it collapses the wave function into its eigenbasis, x's eigenbasis, and that is plus or minus, and that happens with some probability, which here is half. Why is it half? I'll come to that. So x, so the spin along x direction, the spin angular momentum operator along x direction is described for a spin half particle using Pauli X operator. So this is the X operator, and the X operator has eigenvector. Sigma X operator has two eigenvectors. So when I do measurement, when I apply magnetic field along the X direction, I'm doing measurement in that direction, like of the measurement of the spin along the X direction. So it will collapse on the eigenstate of the spin X operators. Okay. So there are two eigenstates, the plus state and minus state, and this is the plus state. So if I represent this, so we had in the Z basis, we said this is how we're going to represent the plus and minus states, like the two eigenvectors of the Z operator in the Z. if I do measurement, these are the outcomes that in the Z direction. These are the outcomes I get. Now, if I do measurement in the X direction, these are the outcomes that I'll get. Okay. So what happened here is the state here is what? Zero state, right? No, one state. So the state that we plugged in here was one. Now I can write the one state as a linear combination. Yeah, as a linear combination of the Z basis. So the plus state, the spin that points downward is actually like the in the Z direction. If it's pointing downwards, this is the state, and that state in the X form looks like this. So when I do a measurement in the X along the X direction, it will basically collapse onto these states. I'll get with half probability, I'll get plus, and with half probability, I'll get minus. Is that clear? Does anyone have any confusion here? Jagdish, are you clear with this idea?
Yes, yes.
Okay. Okay, so let's do this again. So if I send plus, like particle plus, which means it's an eigenvector of sigma x, right? So if I send an eigenvector of sigma x, and if I do measurement in z direction, what we saw is with half probability, I'll get zero state, and with half probability, I'll get one state, right? If I measure in z direction. Now, so these are the two beams that we had. If I take the up beam and apply sigma z again, I'll just get zero again. Like it'll go up again, and likewise the other beam. So those beam, the state does not change because the measurements are commuting. Sigma z commutes with sigma z, so they don't change. It doesn't have to further collapse. They're eigenstates of the operators. Now instead, if I did something like if I started from plus, which is 0, plus 1 divided by root 2, and apply sigma z of measurement, this is again sigma z. Again, I'll get with half probability, I'll get 0. With half probability, I'll get 1. And if I send this beam through uh, sigma x, right, what I'll get is with half probability. So this is half. So let's say I had n of them. Like I sent n copies. So what this means is there'll be n by 2 of 0 and n by 2 of 0, right? So here again there are n by 2, 0 and n by 2, 1. Now if I do this, what we saw is the 0 would with 50% probability give me the plus state. So I'm sending n copies again, let's say. So when I did Z measurement, half of them become 0 and the other half became 1. But after Z measurement, if I do X measurement, they don't commute. So what happens is half of these, which is like n by 4 of them, right, would become plus state, and n by 4 of them would become minus state. Likewise, if I do here, if I do sigma, uh, yeah, sigma X measurement here, n by like half of them, which means n by 4 of them would be plus, n by 4 of them would be minus, right? So these are the two beams that we'll get. Is that okay? That's what, so yeah, that's this part of the experiment. Now, where does mid state come from, right? So this is when I know, like I've kept track of which direction the spins went after its measurement. But let's say I'm a bad experimentalist, just like my handwriting. I also do experiments very untidily. So then what happens is there's an oven from which There are particles coming in. I do a Z measurement. Let's forget about oven. So I have, let's say, plus state coming in from somewhere. I prepared it. If I send it through this, you know, north south in the Z direction with 50, I'll get zero state, and with 50, I get one state, right? So what it means is, let's say I do this. I send this particle in sequence. So I send like one, two, dot 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 up to n of them. So when I do the measurement along the Z direction, let's say the first one collapsed to zero. Like first one went up. The second, let's say, went down. The third went up. The fourth went up, and so on. It's randomly happening, right? So these zeros mean these are the ones that went up, and the ones mean those are the ones that went down. So I know half of them, n by 2, are in zero state, and n by 2 are in one state. That's all I can say. I cannot predict which one will go up or which one will go down. That's randomly happening. But I know half of them will go up and half of them will go down, right? Is that fine? So this is if I keep track of which one is going up and which one is going down. But let's say I forgot which one, like, so they're split in two directions, and then they're moving parallelly. And then I forgot which one was which beam. I don't know which one is zero and which one is one. If I forgot to label, this is if I label them. So if I label them, I know first one is zero, second one is in one. Like first one went down, second one up, third one and fourth one down. Right. So first, third, and fourth are in zero state. Second, and I don't know, there are n by 2 of them in up state, like which went up, and n by 2 which went down. This is what I know. And I know if I keep track of the beams, I can label them and say which of them are up and which of them are down. Now, if I don't label them, all I know is n by 2 of them are 0 and n by 2 of 1, right? So if we don't label, then all we have is n by 2 are in 0. This is with labeling. With labeling, as in I know what the outcome of the measurement is. Like I've kept track of which one is which. So without labeling, all I can say is n by 2 of them are in zero state and n by 2 are in one state, right? So if I give you something of this form, a mixture of 0 and 1. So these are not, so remember, if after the measurement, the two beams, if I combine the two beams, that is not equal to the 0 plus 1 by root 2 superposition. This will also give me half probability for both of them. But these two states are not equivalent. This is a mixture, classical mixture. This probability of getting 0 and 1 came because I forgot to label them. It's a mistake on my side. Okay. So this is a classical probability. This probability is different from the wave function collapse arguments that we have, which is an intrinsic quantum mechanical probability. But here it's a classical probability because I forgot to label them. Is that fine with everyone? Okay. So the question is, how do we describe these scenarios? Like if you don't have labels, if you forgot, or let's say I did some experiment, I have up and down beams, and I give them these particles. So I know I've segregated them. Now these particles are either in up or down state. But when I give it to you, you don't know which one is up and which one is down. But what you know is that half of them are up and half of them are down. Right? So how would you represent the state of uh, this state? That's the question that we're going to address. Okay. Okay. So let's just generalize this and then try to find a way of discussing, the scenario. So if I had a pure state, let's say I know my quantum state is in some state psi, right? The expectation value of any operator, I would just write it as psi a psi, right? But instead, let's say someone did some measurement and then they got outcome n with some probability pn. Okay, so this is the probability, and this is the outcome of the measurement, right? In this case, how would I represent the expectation value of an operator? So why is expectation value important, right? So in when we do measurement, so when I did the Stern-Gerlach experiment, what I actually have is the ratio, right? So let's say, so what I can, what all, the only thing I can measure is the expectation value observable. So when I do measurement along z direction, what I'm measuring is actually this quantity. What is the expect, like, so if I'm given some state psi, right? So when I say I measure along the sigma z, when I do measurement along sigma z direction, what I actually get is this psi sigma z psi. How is that helpful? Let's just do this. So let's say psi is some a0 plus some b1 divided by normalization. So let's say a and b are probabilities. No, square of a and b are, gives me the probability to be in 0 and 1 state, right? So when I do the measurement, what I actually get as an outcome is this quantity, sigma z psi, which you can easily find to be mod a square mod b square minus mod a square. Okay, so mod b square minus mod a square. So this is the outcome that I get, right? Let me just write this as root of p0. P0 and p1 are the probabilities to be in 0 and 1. So what I will get is P1 minus P2. This is the expectation of sigma z. If I know expectation of sigma z, I also know this condition P1 plus P2 is equal to 1, right? So so if I know the expectation of sigma z and the fact that total probability has to be 1, all I need is if I'm given this expectation, I can find what these probabilities are. The probability of going up and down is. So when I do the measurement, my outcome is actually expectation values of operators. That's the thing that I'm actually measuring, the average of an uh, average quantities of any observable that I'm measuring. If I do sigma set, the same argument goes through. Okay. So these are the quantities that are outcomes of measurement. These are the only quantities that we can uh, talk about, like that experimentalists have access to in quantum experiments. Okay. So instead of pure state, if we had mid state, how would we talk about this expectation? Okay. So that's what we're gonna do now. Okay, let me leave the question mark here. Uh, so we know here that if the state was n, the expectation is nothing but NaN, right? Now n happens with some probability Pn, right? Which means with some probability Pn, I would get the expectation NaN. Like, do you agree with this? If you don't, let me know. If this is the case, so this Pn sum over n Pn, this is the probability. So it is a sum up to one. So with Pn probability, I will get this expectation. This
Sir,
district,
what?
like, yeah.
So, how you're writing this? Cat n is expectation of A. Uh, how
Which line? You
this
mean this line?
this line? Yeah.
Yeah. So I'm saying, okay, let's do. So let's say I have a system in the state n, right?
Okay. Hmm.
So what is the expectation value of this operator A in the state n?
Okay.
This is the definition, right?
What is the expectation of this state
What is the
to be
expectation of this
A?
observable when
This
I have the
observable.
state n? Yeah. Okay. So if I have the plus state, for instance, Let's do an example. So if I have the plus state, which is 0 plus 1 by root 2, and if I do measurement along z direction, what is the average z? Let's just do sigma z, right? So this is 1, 1, 1 by root 2. So average of sigma z is 1, 1. Sigma z is 1, 0, 0 minus 1, 1, 1. And there's a 1 by root 2 here, 1 by root 2 here.
Okay.
This is equal to, uh,
Yeah, that is fine, sir.
yeah, this will come out to be 0.
Yeah.
Okay. So what that means is for the plus state, average sigma z is 0. So that's what you
Hmm.
saw. If I have plus state, if I do sigma z measurement, half of them will be 0, half of them will be 1, which means on
Hmm.
average, there's no z value, right? The total angular momentum is the average angular momentum along z direction is 0 because half of them have eigenvalue 1, half them have eigenvalue minus 1. Is that fine?
Yes. Okay.
Okay. So if my state uh, was a pure was a proper pure quantum state n, right? The expectation value of an observable, this is how I compute it. Now instead, if I did not know if it was an n, so you're giving me some state. So if, with some probability Pn, you're giving me, let's say, state n, right? Then if I compute expectation again in this form, it will be what? With some probability Pn, I will get the outcome. I'll get the average, and if I do my experiments, right? Some over n. Okay. Now we know the completeness theorem that like, so let's take an arbitrary basis. Okay, so we know from the completeness relation that if I do this for all possible k, it has to be identity, right? So I wait, let me rewrite. So expectation value of an operator A is sum over n Pn in a n, which I can write as sum over n Pn. I'll insert an identity operator here. Identity does not do anything, so no harm. But I can expand identity as sum over some k out of product of k in some basis. If I do that, it will be n k. So then it will be sum over k, and then I'll also the second identity I'll expand it as k prime, k prime, and the state n. If I pull out the summation outside, it will be sum over n k prime Pn. Uh, so okay, let me use colors. This n and k in the product would be n k, and then this and this together will give me k a k prime, and this with this will give me k prime n. Is that okay? So these are numbers. Uh, I can expand this average in this form. Hello, can you guys see my screen? Hello?
Yes, sir, it is visible. We can see.
Okay,
Yes,
yeah.
sir.
Okay, so my screen froze for a second, so I thought you were not able to see. So do you follow what's on the screen? Did you guys see the steps? Okay, I'll just explain it if didn't come through. So what we do is we have this quantity. So I basically insert two identities in between I here, but we know from the completeness relation, identity can be expanded in the base in a basis in this form as an outer product of basis states. So I insert like I replace those identity by that that expression, and then if I move around, if I take the summation outside and do some massaging, I can basically write this last line. Okay, now so these are basically all complex numbers, or this is a real number. No, these are all basically complex numbers. So since they're numbers, I don't need to worry about commuting. I can move them around. I can write sum over n k prime pn. Uh, yeah. So I'll write k a k prime, which came from here, and then k prime n, which came from here, and then n k, which came from here. Okay. The next step, I'll take one summation inside. I don't need this sum. I can which one? Yeah. So it'll be pn k a. If I take the k prime summation here, k prime outer product k prime, and then n k. So this nk outside. So this is basically identity. So this is a trick that we always use in quantum mechanics. Like whenever you want to find expectation, if there is some sort of overlap inside, or even if you want to find, uh, anywhere if you have identity, I can put identity anywhere because identity doesn't do anything to the state or the operators. So if I have this expansion, if I use this complete basis idea, so I can put any complete basis inside and then move things around to get to do calculations like the one that I'm doing right here. Right now, this whole thing is identity, so I can just substitute identity and then not talk about it. So this further simplifies, and what I'm left with is sum over nk pn k a, no, just k here, yeah, n k. Now I'll do a bit more rearrangement. Sorry. Yeah, this is sum over k n as well, n and k. Now if I do one more set of rearrangement, what I'll get is if this k from here, this a, and then I move the pn inside. Pn is a probability, so it's a number. So the summation over n, pn, n outer product n, acting on k, right? Now if I define, so from this I can write sum over k, k, a, rho, k. So I've defined this quantity to be rho, to be this rho. Okay. Now there's a okay. So if I there's the mathematical thing that I want to tell you. So if I have trace of an operator z, let's say I have some arbitrary operator z, the trace of z is equal to basically sum of diagonal elements of z. Okay, sum over I zi zi. So I take if I have a matrix z11, z12, so on, z21, Z2, 2, and so on, right? So trace of Z is basically sum of the diagonal elements. Okay, and this can also be, there's another way of writing trace, which is if I need to take a full basis and then write this. So K Z K. So this is another way of doing trace. So if K forms a the set of all K's form a full basis for the Hilbert space or the space that we are dealing with. So this is another way of writing the trace of a matrix or an operator. Okay. So if you look here, this looks like trace of a row, right? If I associate a row with Z, that looks like that. So I can write this as trace. Is there anyone here who hasn't seen trace before, like who have not worked with trace in any course or anywhere? Could you raise your hands, please? Because it's very important as you go along. There are some, like if you use density matrix formalism, trace will be all over the place. Okay. Jagdish has not done trace. Anyone else? Is it just one person? Okay. Okay, there are a couple of people. So what I'll do is in the next session, I'll start with properties of trace so that when we get to things like entropy and relative entropy and things like that, this will pop up every now and then. So it'll be helpful to kind of know how to deal with trace. Okay. Right now, just understand that if I have expectation value of an operator, so right now for the time being, just take this as the definition. So this is how you find expectation. So for any ensemble, right? So this operator row now has all the information. So what did we start with? So we had this ensemble, right? We knew that we're given state n with some probability Pn, and then we wanted to find the expectation value or the mean value of an observable A. So what we have done through this long tedious calculation is that so this quantity here has that information Pn and information that's now encoded in row, and A is just the observable that we are interested in, right? So if you're when we're in quantum mechanics, we're interested mostly in the expectation values of observables. So to find expectation values, you don't need to keep track of what happens to each of the state. All we need to know is the state. Like if I'm given an ensemble of this form with Pn, I get the state n. I can define this quantity rho, which is sum over n Pn n outer product n, right? So this rho encodes the information about this ensemble. Sorry, this is this. Right? So if I'm not given a pure quantum state, if I'm given a mixture like this, if I'm given a classical mixture, right? So it's a mixture in the sense that it's a mix of all n states. Like n here represent quantum, like different quantum states, right? So these quantum states are mixed with probability Pn. So this is what you mean by mid state. So if I'm given a mid state of this form, I can study what all the expectation values associated with the state using this quantity called the density operator or the density matrix rho, and that's defined in this form. Okay, let's just do some examples so that you know how to deal with density matrices. So if I'm given, so here if I'm given this pure state 0 with p equal to 1, right? With full probability, I'm giving you this exact state 0, which means with probability 1, you have state 0 with you, right? So what did I tell you? If I have Pn coming with probability n, then my density matrix is this with pre-n is of this form. So here it's what? It's with 1 times outer product of 0, 0. This is my density matrix. So pure states, density matrix is just outer product of the state with itself. Okay. So so we knew that we represented this state as 0, 1. That means, wait, did I go for? Yeah, so it's right, which means this is nothing but transpose complex conjugate transpose. We'll have this form. So if I just substitute it here, this is the density matrix corresponding to the state 0. So there are two ways of what I'm telling you is if I give you a pure state, a proper quantum state 0, there are two ways of representing it. One as a column vector like this, or as a matrix like this. These are all both equivalent ways of describing the state. Right? So if I had this, if I want to compute expectation value of, let's say, give me an operator, like one of the Pauli operators, which one would you like to compute? Okay, let's take Z. Z is easy. So if I need to find expectation value of sigma Z in this case, if I'm looking at the pure state perspective, this is what I should compute, right? So it's basically 0, 1, 1, 0, 0, minus 1. This is sigma Z operator. This is this part, and then there is 0, 1, which is this part. Okay. And this is, if I do the matrix multiplication, 0, 0, 0, minus 1, acting on 0, 1, and it'll just become minus 1. Now, if I do it from the density matrix point of view, sigma Z, what did I tell you? This is what trace of the observable, which is sigma Z here, times the state rho. So this is rho here, okay, which is trace of the matrix 0, 1, 0, 0, minus 1 times the rho. Rho is now 0, 0, 0, 1 from here. I need to find trace of that. This is, if I do the multiplication, so this is trace of this matrix. So if I do the matrix multiplication, I'll get 0, 0, 0, minus 1. It's trace of this matrix. Trace of the matrix is sum of the diagonal elements. So this is 0 plus minus 1, which is minus 1. Right? So these are two ways of finding expectation value of sigma z in this case. For any arbitrary state operators, I can do this. So for pure state, it doesn't make much of a difference. Right? If I had plus state, if I had plus state, for instance, the density matrix would look like this. Okay. Again, if I compute plus sigma z plus, this will be 1 by root 2, 1, 1, 1, 0, 0, minus 1, 1, 1, 1 by root 2. And what will this be? You can calculate. It's 1 by 2, 1, 0, no, 1 minus 1. I mean, you can do the calculation. It'll come out to be 0. Okay. So this is, instead I can, so this is rho plus. So if I did sigma z, I can also do trace of sigma z is 1, 0, 0, minus 1 times 1, 1, 1, 1 with a 1 by 2 here. So 1 by 2 will come out. If I do the multiplication, I'll find it to be trace of uh, minus 1. So this is half, or let's just keep the half inside. Trace of this is basically sum of diagonal values, diagonal elements of the matrix, as I said. So here it's half minus half, which is zero again. So this is another way of computing. So for pure state, it doesn't make any difference. But if I have mid state, which means if I'm given an ensemble of this form with some probability Pn, I'm given the state n, right? So this is now, let's take this example. So let's do some different probabilities. So with probability 1 by 3, I get the state 0, and with probability 2 by 3, I get state 1, right? So my density matrix rho is what? With probability 1 by 3, I get the state 0. So I do outer product of 0, 0. And add to it, with probability 2 by 3, I'll get the state 1, 1. Okay? So this is my density matrix. So this will be 1 by 3, 0, 0, 0, 1, plus 2 by 3, 1, 0, 0, 0. This is nothing but, yeah, 2 by 3, 0, 0, 1 by 3. So this now gives me, so if I had a mixture, classical mixture, previously I did not have any way of representing my state properly. Now I do. This is how we represent the state. Okay, and given this representation, I can find expectation values of operator sigma z, for instance, as trace of sigma z with rho, which is trace of sigma z is 1, 0, 0, minus 1, 2 by 3, 0, 0, 1 by 3, which is again trace of, if I do the multiplication, I think we'll get 2 by 3 and 1 by 3, 0, 0, minus, and this will come out to be 1 by 3. Right? So this is, so here the density matrix way of representing the state is gives you, a concrete way of describing the system. Okay? Does anyone have any questions now? Someone had a question about density matrix in the beginning, right? Is that cleared, or do you still have the question?
Sir has represented in the video in different form, I think.
Okay.
Mm,
Okay, let me.
it is, yeah, I understood, I think.
Okay.
Yeah, let it be, sir. I'll see.
Okay. So maybe let's say maybe after the session, uh, I can maybe look at the video and then we could have a small chat.
Okay.
Okay. Yeah. Yes, Ambarish.
Sir,
You have a
I have
question?
a question. Sir,
Yes.
that is the dense. I have watched the lecture video and also I have the solve few problems of the assignments, and
Okay.
I have noticed here, sir. Sir, my question is that according to density matrix formalism approach, what is the actually what is the link between entropy? My first question, and the second question is that in this approach density matrix, how it is going to the ensemble actually it is a starting of a statistical quantum mechanics, am I right or not?
Yes, this is one way of doing statistical statistical
Quantum
mechanics.
statistical mechanics.
Yeah.
Huh,
So
huh.
in classical statistical mechanics, so there are two ways of approaching like two places where we need mid state. One is when we study open quantum systems. Two is when we do uh, statistical mechanics. So what I'm describing right now is the toolkit for statistical mechanics point of looking at the problem. Okay.
Huh, huh, huh.
So that was one question, right? And the second one
Yes.
was how is it related to entropy? So
Huh,
if I take a pure quantum state, they have zero entropy. So the entropy of a quantum state comes because of mixedness. When I have classical
Because of
probabilities, mixedness because of this ensemble. Like when there's a
Okay,
classical,
okay.
yeah. Were you saying something?
No, 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 no. I've
Yeah, yeah.
watched the.
So
Yeah.
I think we'll deal with that in the next session or the one after that. I don't remember.
Okay,
Uh,
sir.
there was one quantum information. I think it was fourth week. So I think it was fourth week. Third was angular momentum. Fourth was quantum information. So there we'll do entropy and things like that properly. Is
Okay,
that
sir.
fine?
Okay, sir.
Yeah.
Okay, sir. Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Yeah. Yeah.
So one minute. So
Yeah.
here, if we have to find the probability of finding the system in zeroth state,
Yes. How do you do that?
yeah,
Okay. Let's do. Shall I do with this example, or do you want me to do it for another case?
yeah, with the same example I want.
Yeah. Yeah. Okay. So the probability to find the particle in any state psi is basically this. This is probability to find psi given the state is rho. So what do I we can so from the ensemble we know directly, right? The probability to find 0 is 1 by 3 and probability to find 1 is 2 by 3, right? That's we know that from ensemble definitely. Now when we wrote the density matrix, if you're not given ensemble, if you're instead given the density matrix, how would you find that? So this is how you find it. So P0 is 0 rho 0, which is 0 1. Did I? No, yeah, 0 1. And what is rho again? It's 2 by 3, 1 by 3, 0 0. And then there's like 0 1 here, right? Uh, excuse me, I'll be back in 1 second. Yeah, sorry. So I was saying, so yeah, what would this come out to be? So this will be 0, 1 by 3, no, 1 by 3, and 0 1, which will be 1 by 3, right? So we retrieved what we already knew because we had ensemble with 1 by 3, 0 and 2 by 3, 1. So this is how you, is that fine?
Okay, sir.
Okay.
A sir
So,
has written formula of this
mhm.
with some probability also, means summation pi, and then he's taking this zero row zero, means yeah. So that is what I'm not able to understand. So whenever you find time, you can look into that.
Just give me a second. Let me check. Okay. Uh,
So it
okay.
is
Yeah.
at the 14th minute of lecture 4. So whenever you get time, you can see it.
Lecture for 14th minute.
Yes.
Okay. Initially, my internet wasn't that good. Right now, sorry. Oh, okay. Okay. Oh, that's what you're asking. Okay.
Finding
Okay. Yeah. Yeah, I
difficulty
understand.
in presentation or something, I think.
Yeah. Yeah, I'll do. So his notation is slightly different. So what I wrote till now is that our ensemble is Pn. With Pn, I'll get state n, right?
Yes.
So what he wrote is with Pi, you get the state phi I.
Yes.
Okay.
Pi j he has written. Okay.
Yeah,
Yeah.
phi j. So with Pj, you get phi j. All right.
PI with 5J. Yeah, something he wrote like
Ha,
that. PI.
that's a
Yeah.
typo. All of them have to be same index.
Yes,
Okay. So it's either PI 5I or PJ 5J. It cannot be I and J. That's wrong.
that's
It's
wrong,
a
no?
it's a
Have you
slight
written
mistake
that?
that he made. Yeah, yeah.
Yeah, okay. Then he is doing this probability of finding a system in 5J.
Yes. So I'll come to that. So uh, can I do it in my notation so that it'll be consistent? Okay. So
Okay.
J means N. That's all. 5J means N. J means N. That's it. Okay. So there's this notion of projection operator. So I can define projection operator along n direction, any state psi. Like if I'm given some state psi,
Hmm. Yeah, projection operator can be written this way.
yeah,
Yeah.
this is what I call as projection operator. Now,
Hmm.
probability of getting n is basically trace of the projection operator of n times what the state is. Or in general, the probability to get state psi is trace of the projection operator psi times rho. Okay.
One second, sir.
Yes.
You have written the trace of probability and okay, fine.
No, trace. No,
Uh,
wait. What did you
but
say?
before that, we were doing this trace of rho with
So
sigma z, some
yeah,
vector.
so instead of observable A, I use the projection operator. That's it. Then I'll get probability,
Okay, probability. Okay, instead of observable, we are writing here this
the
no
projection operators.
projection operator. Okay, fine.
Yes. Then I'll get the probability to be in that projected state. Okay. Yeah. So yeah, that's it. I can think of projection operators as a kind of observable, which tells me whether my particle is in that subspace or not. If it is in
So
that
we can
subspace, it will
use
give me
here
one.
also.
Yeah.
Means instead of writing this observable, we can write the projection operator.
Yes, I
No.
can. I'll define it. So let's say I want to know if my particle is in zero state. So what I define is an observable of this form. This is a Hermitian operator, right? So this is what I define as my observable A,
Yes.
right?
Oh,
So what this tells me is if my particle is in zero state, I'll get outcome one. If my particle is not in one, if it's in a one state, it'll give me zero as outcome. So this will directly tell me, this is an observable that I should look for if I want to find the probabilities. Does that explain?
okay.
Okay.
Okay, fine.
So your doubt is clear now.
Yes.
Okay, good. Feel free to interrupt or ask questions whenever when you are stuck or confused or anything. Okay. So yeah, so if I have given a definite state psi, I'll just summarize what we just said. So if I am given the state rho and given state rho and we want probability to be in state, let's say psi, then it's given by p psi is equal to either I can do this psi rho psi or it's equivalent to writing this phrase psi rho, right? And this is called the projection operator along z direction. So when I write normal p, it's probability. When I write this with a double line, vertical line, that's a projection operator. Okay. Yeah. Now let's say I have a okay. Since we're doing this, I'll also do something generalized. Let's say I have a n level system, 0, 1, 3, 4 level. Let's say 2, 4. So these are my possible basis states, right? And I want to know if I am in this if I'm in the ground state, like so let's say 0 is ground state, 1 is first iterative state, 2 is second iterative state, and 3 is third iterative state, right? And what I'm interested in is knowing whether I'm in the ground state, or in one of the excited state, right? This is a very valid question to ask, whether I'm in the ground state or excited state. So uh, for the ground state, I can define the projection P ground to be 0, 0. And for the excited state, P excited, I'll define as, so it can be in one state, like one state, or two state, or three state. So I add the projectors on corresponding to the, three other states, right? Now, if I'm given that system is in some state rho, then probability to be in ground state is trace Pg times rho, and probability to be in excited state, any of the excited state, I don't know which one, any of the excited state is Pe times rho. And depending on what I'm interested in. Now I said I want to know if it's in ground state or any of one of the excited state. I don't care which excited state it is. If I do care about which excited state it is, I have to define projector operators correspondingly, which you can do. Okay.
So, sir, this is a case when we are not having observables, no?
What do
Previously,
you mean by
previously you were explaining with the observable, no? Here we do, as we do not have the observable, we are writing it in the form of projection of the
no,
state. Is that the
no,
thing?
no. Wait, let me. There's something that I mentioned a bit earlier.
Not
Just
in this pure state, makes the state.
I'm trying to go somewhere. It's something I did ages ago.
Yeah,
So I
just before it only.
so there's if you remember I told you this, right? So if I have uh okay Stern Gerlach, so if you tell me the probability P0 and P1, I know that P0 plus P1 is equal to 1, right? So what I need to know is P0 minus P1. This is what I observe, which is the expression of sigma z. So what I experimentally observe is this quantity, sigma z, and find the expectation value. If I know expectation of sigma z, I can tell you what exactly P0 and P1 is. Does that make sense?
So can you repeat once?
So, so what I
Huh.
want to know is
Mm.
what is the probability to be in zero state or one state.
Yeah.
But I don't know, like, so for that you use like mathematically you can use this projection operator idea. But how do you do it experimentally, right? So what you do is you find expectation of the sigma z operator,
Yeah.
and and it will be this thing, P0 minus P1. But P0 is the probability to be in zero state, and P1 is the probability to be in one state. I also know P0 plus P1 is 1. So from this I can write P0 is what? Sigma z plus 1 divided by 2. And P1 is sigma z, no, 1 minus expectation of sigma z divided by 2. Okay. So even if I'm looking for probabilities, experimentally what I would do is find expectation values of observables.
Okay.
Okay. At the end of the day. So if I want to do this kind of thing, I'll have to define an observable. Uh, Let me say, I'll define something like A is equal to PG minus PE. Okay. This is a bit advanced, but let's just do it. The course title itself has advanced, so why not? So, so PG is the projection operator onto the ground state, and PE is the projection operator onto the excited state. So if I look at expectation of A in this state rho, so nothing but trace of A rho. Okay, so this is trace of A is PG minus PE rho, right? Which comes out to be what? So trace has this property. Okay, this is property trace of A plus B is trace of A plus trace of B. So what that means is I can write this trace of PG row minus PE row, which using the above property can be written as PG row minus trace of PE row. Right? So the first thing is uh, the probability. The first quantity is probability to be from the mathematics we know, like the projection operator, expectation of projection operator. So this is what we defined as PG and this is PE. So if I construct this observable, I need this. I don't know how I do it experimentally. So if I can think of an observable of this sort, I'll find the expectation of this observable that will tell me what PG minus PE is. Right? So PG is basically, since PG plus PE is 1, this plus 1 by 2 is PG and PE is 1 minus expectation of A uh, divided by 2. Is that fine? So my point is this way of writing is a mathematical way of doing it. Experimentally, you have other, like when you do it practically, there are other caveats attached to it.
Okay, sir.
Okay. Yeah. Okay. Yeah, I'll briefly describe some properties of density matrix and time evolution. After this, we're done. And maybe I had some problems prepared, but let's see. Depending on time, we'll figure out something out. So, uh, so let's say we're given a density matrix rho. Okay, we have an ensemble from which we wrote down the density matrix. So we know this PNs here are probabilities. We said that, right? So that what that means is uh, they cannot be negative. They're either 0 or positive. So this is property. So a matrix which satisfies this property is called positive. Okay, something happened. Positive semi-definite. So density matrices. Okay, let's just write them properly. So density matrices rho is positive semi-definite. What that means is if I'm given any state psi, it doesn't matter psi. Psi can be anything. Psi rho psi is a positive semi-definite quantity. It's greater than or equal to 0. So this is what we know. This is the probability to find particle in the state psi, right? This is what we called trace of projector onto the state psi times rho. The discussion that we had. So this is basically the probability. So this quantity here gives us the probability to find the state rho. If I'm given an ensemble which is represented by this density matrix rho, the probability to find it in the state psi is given by this expression, and it has to be positive because of the probability, positive or 0, right? So this is basically what positive semi-definiteness implies. So these are basically properties of density matrices. Now let's look at the second one. If I take uh, rho dagger, what happens, right? So rho dagger is basically, so what is rho? Rho is sum over n, Pn, Nn, where Pn's are probabilities, so they're real numbers. Dagger of this is equal to sum over n, Pn dagger, which is Pn star, complex conjugate of Pn, times N dagger. So if I have a number a plus ib, dagger of that is a minus ib, which is nothing but a plus ib star, like the complex conjugate that we are usually used to. And if I have some object of this form, nm, the complex conjugate of that is m n. Okay, since this is n and here, okay, I should have written this somewhere else. Sorry. Move it up. So what this comes out to be, since Pn is a real number, the complex conjugate is also real. So it's just Pn. Since it's n out of, if I take dagger, it will be n again. So this is rho itself. So what this means is the density matrix is a Hermitian. Right? If I have the rho dagger equal to rho implies Hermitian. Okay. There's also one more property which I'll let you prove. Since we're not done trace properly, I won't do it today. But trace of rho, those who know how to deal with the trace can show that trace of rho is 1. So it's normalized. So this will be sum of all the probabilities that you have. Okay. So yeah, so the last thing I want to do today is how, so this is how you, so let's say we are decided to describe time evolution of like our quantum system using density matrix. Now, how do you describe time evolution of this state? So we know if you have a physical system, it can evolve in time. So how do we do that? So if I have pure state, how do you describe time evolution? We have time dependent Schrodinger equation. What is that? It's basically I h cut d psi by dt is equal to h psi. We all know this, right? Okay. Now, if I take diagram of this whole equation, right? I h cut d psi by dt. If I take Hermitian conjugate of all of this is h psi Hermitian conjugate. So the I will pick up a minus sign because Hermitian conjugate of a complex number is basically conjugate of the complex number. D psi by dt, d by dt, nothing happens to it. Psi, so if I had psi dagger, this is psi, it just changes inwards. This becomes this is equal to, so if I have AB whole dagger, this becomes B dagger A. So I'll send all these notes, so you don't need to write down all these formulas. So I'll try to upload it today or tomorrow. You'll have access to it within a week or so. I haven't done the previous session as well. I'll do that today itself. So this will be, so yeah, if A acting on psi whole dagger, it becomes what? So the first thing is if I have sequence of A, B, when I take dagger, they swap, like you have to invert the positions. So psi goes to the left and this, so from this property, this is whatever is the dagger of psi times A dagger, right? And this is from the first property, psi dagger, A dagger. So the right side would be psi h dagger. H dagger is h itself because h is a Hermitian operator. So we get this. I'll call this equation 1 and this equation 2. Now multiply 1 with psi. Right? So what do we get? I h cut. No, don't do that. Don't do that. So what is the density matrix? It's of this form, right? Sum over I. Let's just write the form in Sir has written in his notes. Pi, phi I, phi I, why phi I is some basis, right? So d rho by dt is the quantity that we're interested in, which is sum over I, pi, d by dt of phi I, which is sum over I, pi. Okay, wait. So we need to figure out what this quantity is. So let's just focus on that. Uh, so we want to know d by dt of phi I. This is nothing but phi, yeah, um, d by dt. I'm just using the chain rule plus now if I substitute from the above equation, if I substitute 2 here and 1 here, right? So I have to invert. So I have to take the ith squared to the other side in this equation and this equation. So basically, I have d phi by dt form and like of the bra form and ket form. I've defined them already. So if I do that substitution, what I can show is phi I. What is the ket? Ket is ith squared goes to the other side. I goes up. I by h squared phi I h. And the other one would be minus I by h squared uh, h phi I. Now grouping things together, it's I by h squared. What am I left with? Phi I, h minus h phi I is nothing but I by h squared, commutator of phi I, comma, h, right? Now I can substitute that in this expression. So d rho by dt is equal to sum over I pi d by dt of phi I, which we now found to be sum over I pi, this I by h squared phi I, comma h. I can take the summation and the pi inside and write this as I by h squared commutator of sum over I pi phi I, comma h. But this is nothing but rho. Um, I think I missed a minus sign somewhere. Let me check my notes. Okay, I don't know where I missed it, but I missed a minus sign somewhere. So if I got minus sign. Oh no, I have not. I have not. Okay, sorry, my bad. It's correct. There's no sign mistake. So I usually remember this formula in this form: minus I by h squared h comma rho. So this is because a comma b is equal to minus b comma a. So I remember this form of the formula, but that had a minus. Okay. So this is how if I have a mid state described by the density matrix rho, and if it's evolving under so there's no dissipation or anything, it's still a closed system. So this is how the time evolution of rho looks like. Is that fine? And this equation, this is d rho by dt equal to minus I by h squared h comma rho. This is called von Neumann Liouville equation. So those who have done classical mechanics, I have an interesting connection that I would like to make. So when you do classical mechanics, when you do Lagrangian and move to Hamiltonian dynamics, we know that the probability distribution, evolution of probability distribution, d by dt of probability distribution, is given by the Poisson bracket of Hamiltonian. I'm not sure if it's there's it's possible that there's a minus sign. So this is equal to, I think, dou by dou x of A, dou by dou P of P minus uh, dou by dou P of H, dou by dou A of P. No, I'm not sure about the exact structure, but Poisson bracket has a form like this. So this is called the Liouville equation in classical mechanics, right? So if I have yeah, does anyone have any comment?
No, sir. Yes, lovely theorem. I've
Yeah, Liouville theorem, exactly. So if you have a probability
yes.
distribution, so let's say I take a particle moving in one dimension, right? So it can be described by position and momentum of the particle. Now, if I know exactly how where the particle is, I can tell how it evolves in time. But instead, if I don't know where exact position is, all I have is a mixture. I know it's in this blob. I don't know where this is, but I have a distribution. I know with what probability I can find it here, with what probability I can find it here, and so on. So I know it's inside this region, but with some probability. There's a probability distribution in the x and p variables. If I'm given this as my initial state, if I'm given this as my initial state, how do I describe the dynamics of the probability, right? In classical mechanics, this is given by the Liouville equation or the Liouville theorem or Liouville equation, right? And this has lots of consequences like this is for closed system evolution because it's driven by Hamiltonian. So the phase space volume would be conserved in the sense that if I do, let's say this evolves in time. So this, like after some time, becomes something like this, and then it becomes this. And what's given is the volume of this blob would remain constant in time. So this is t equal to 0, this is t1, this is t2, and so on. There are like several physics that comes with it. So this equation, von Neumann-Liouville equation, is the quantum mechanical version of the same thing, right? Here, rho is the density matrix which describes the state, just like the probability distribution describes the state in the phase space. H is the Hamiltonian. And so, yeah, there's a complete, like, there's a correspondence between these two, which we can make. Is that fine? Does anyone have any questions? So, in the first session, first week, Sir talks about representation in position and momentum basis. I briefly described it in the last session, but I felt like it was a bit confusing. So I've made notes on it, but I'm not sure if I should do it. Like, does anyone confused about it still now? Like the position momentum representation and how the x and p operator comes about, how p operator is represented minus I dou by dou x and so on. Do you want me to do it now, or it's already 6:45? It's been 1 hour and 45 minutes. Should I continue or shall we stop here? What do you guys say? I'll share the notes and I'll also be I'm recording the video, so it will be posted on YouTube. You can access it from there.
Thank you.
So yeah, so if you want me to continue, can you raise your hands? Those who want me to continue? Okay, there are a couple of people. Okay, so I'll be sharing these notes, and so I think the NPTEL team will share the video lectures and the notes with you probably by next week. So they're compiling it right now. So you'll have access to the lecture, this sessions and the notes soon. So don't worry. So I'll maybe okay, since there are a couple of people who said who are interested in listening, I'll maybe continue for 15 more minutes and then. So those who wants to leave may leave. If you have any questions, you can feel free to stay and ask. I'll be basically talking about representations of quantum states in different bases. Okay, so because it's a bit confusing concept, like when you go from classical mechanics to quantum mechanics, how do you represent a state is a bit messed up. So till now we have been doing mixed states. So this is something that should have come before it, but this is to it. Right? So from here on we'll only be talking about pure states. Okay, which means proper states that we usually learn in quantum mechanics 1 or quantum mechanics 2. Okay, so we know states of a quantum system are described by a vector in a Hilbert space. So let's just assume that we have a Hilbert space H, which is spanned by some vectors phi n. So this phi n forms a set of all phi n's forms a basis, right? So this is just like saying if I take the three-dimensional space, the right. So there's x, y, z direction. So this is a three-dimensional space, right? And these three vectors, unit vectors along x, y, z direction, they form a basis. So phi n's are like x, y, and z, like the unit vectors along x, y, and z. Yes, Mayank, do you have a question? Okay, enough. So x, y, and z are like the basis elements, right? So in quantum mechanics, we typically we sometimes deal with Hilbert spaces that are infinite dimensional. So it's difficult to think of them in terms of these vectors in space, like find a complete analogy, but let's try. So let's say our Hilbert space that we're dealing with is spanned by these vectors phi n, and we assume that they're orthonormal bases. What does that mean? Okay, so what that means is if I take inner product of phi n with phi m, it's delta n. It's a canonical delta function, which means when n equal to m, it's 1. When n not equal to m, it's 0. So this is what orthonormal means. It's a basis because it spans the full, it can span the full Hilbert space, and this is given by the completeness relation. This is something that we used earlier. Completeness. This is orthonormality. Okay. So yeah, so a basis follows these properties. They're not all bases. Like to be a basis, only the second condition is needed. But to form given a basis, we can do something called Gram-Schmidt orthonormalization to find a basis in which these two conditions are satisfied. Okay, this is easy. It's easier to work in this basis, so we'll stick to this kind of basis. Now, so given a state psi, right? What I can do is I can write psi as identity acting on psi. But we said because it forms a basis, we have this completeness relation, which lets me expand identity using this basis, right? In this form, in the form written here. Now, this is an inner product of phi n with the state psi, right? Which is this guy. So when I do an inner product, I get a number, a complex number in this case. Depends on what kind of vector space, Hilbert space you're talking about. But in this particular, in the context of quantum mechanics, we are dealing with complex Hilbert spaces, and hence the inner product will be a complex number. So this is the number. So phi n psi is a complex number. And phi n's are basically the basis states, we know, right? So if I call them as an, there are some numbers which are fixed. So now I can write my state as sum over n, an, phi n. This is how we have been writing our states all along. So given a basis psi, you can represent this form. So this is equivalent. So if I have a vector in normal space, I write it as what? It's some h1 I cap plus h2 j cap plus h3 k cap. I can equivalently represent this as a column vector h1, h2, h3, right? So in this case, what it means is I can write this as, so what I did is I took the coefficients. This is summation. I took all the coefficients and wrote them in a column form. Likewise, since this forms a basis, I can take the coefficients and write them in the column form. All right. But this is not a good way of doing it because, as I said, we are dealing with infinitely many of these states. So the Hilbert space that in the three-dimensional, like in the space that we are dealing with, in the in the space that we live in, is three-dimensional, and we only need to keep track of three numbers. But quantum mechanics, when we look at, there are infinitely many. The basis consists of infinitely many elements, and hence this vector would be infinitely long. Right? There are infinite elements in this column vector, so it's not a very convenient way of representing things. So, yeah, but this is how the intuition comes. Is all I'm saying. Now, if I have an observable operators A, I can put identity on both sides and doing like above calculation, I can, this is how I would write the operator. So if I have in this basis, in the phi n basis, A would look like A11, A12, and so on, A21, so on, right? A22, and where A11, like A and M, is given by this expression. So once I've fixed a basis, so this is very important. So all this is in this basis phi n, right? I've chosen a basis. I don't know. There could be several motivation for doing this, but once I've fixed a basis, I can represent my state as column vectors or in the expanded form, and the operators as matrices. Now the issue is when we look at position, for instance, right? So to represent a point in three-dimensional space, we need three vectors, three variables, x, y, and z coordinates. But in quantum mechanics, we have the idea of superposition. So the way we represent state is very different. So if I'm given a quantum state psi, when I do measurement, I get an outcome. Right? Let's say I do measurement in position. I look at the position of a particle moving in space. It will tell me. Okay, let's do that. Okay. Let's say I have a quantum state psi. Right? It's some state. It's a particle represent representing particle moving in one dimension. So there's only one dimension. It's like there's one coordinate. It's restricted to move on a line, let's say. Now I can ask this question: what is the position of this particle? So this is my axis. Axis my direction. So I can ask what is the position of this particle? Yeah,
Could I tell?
yeah. Go ahead.
Yes, sir. Sir, if I take an operator is Siemens operator x of x cap, and
Yeah,
it's acted over the state of psi vector, and that is gives the position of one dimension x. That is equals to x psi. That is x is our position of
X
the
is the
particle.
position operator, but
Yes, sir.
yeah, I'll tell you. So X is a position operator, but when I do measurement in the X, you're saying do a measurement, right? If I look at where the position of particle is, it'll tell me some number, right? It's at, let's say, 1 meter from the origin or 1 nanometer from the origin. It'll tell me some number, right? Where it is exactly. It'll basically, does that make sense? So I understand where your argument is coming from. So we're going to formalize that. So before that, let's just think about what measuring the position means. So I'm given some arbitrary state psi. When I say I'm measuring the position of the particle, what I mean is I'll get some outcome which says exactly where the particle is. Let's say it tells me it's here, right? So this is one possibility. Let's say this is x1. So the particle is at x1. it's possible that when I do another measurement, it says it's X2, right? So these are independent outcomes. They don't have overlap. Okay. So in quantum mechanics, what happens is I can have states which are not localized. So I could have states like this, which is the distribution. So there's some probability which is given by the height, square of height, which tells me the probability of particle to be here, and there's some other probability to be here, and so on. So the particle can simultaneously be at, in some sense, be at several places. Only when I do measurement, when I measure, what happens is it will collapse onto this state, like this particular state, with some, let's say this height is P S1, P1. So with P1 probability, I'll get this state, right? And let's say this is H2 with probability P2. With P2, I will get this state. Let me give a different color. With Does this make sense? With P2 probability, it will give me outcome H2. Okay. So this is what happens when you do a measurement on a state of this form. It's a quantum state, which is a wave function which is spread across space. So when I do measurement in the position basis, it will collapse onto one of these eigenvalues of the position. That's what you have been saying. Yeah. So we'll come to that. So when I do measurement, I'll get one of these values, right? It will tell me exactly where the position is. So each of these are independent outcomes, and they have to be linearly independent. So what happens in quantum mechanics is that the position set of all possible positions forms a basis, and you can form your Hilbert space using these spaces as linear combination of these vectors. Okay, so that's the position basis, and the property of this position basis. If I am in this exact state, let's say my state is, let me make some space. So my state is exactly here. It's at H naught, right? Particle is the probability of particle to be at found at point H naught is 1, let's say. If that's the case, such states are the eigenstates of the position operators, because I'll get the eigenvalue. It's the eigenstate of the position operator. It'll tell me exactly where the position is. If I have some spread, then it'll be a linear combination of these states. Okay. So the basis is position basis is formed by eigenstates of the position operator H cap. H cap acting on the state H gives me the position, which is what you have been telling. So when H cap acts on H, it will give me the eigenvalue, which tells me where the particle is, and it will still be in that state. And this has the property that if I know exactly the particle is at H, and then it cannot be at H prime, right? So the overlap of the state H with H prime, if H not equal to 0, if H is not H prime, then if my particle is at it means it's not at H prime, right? Am I confusing you guys, or can you tell me if you're following what I'm saying?
Yes, sir, we are following.
Okay. So let's say I have a particle at H, right? Now by this, so this is represented by state H. Now I'm asking what is the probability of finding, given this state, what is the probability of finding the particle in H prime? Right? That will be 0 if H not equal to H prime. Now, when H is equal to H prime, this function is okay. This is wave function. The square of this, okay, that will happen. So this is where the intuition comes from. But since these bases are continuous, there are some subtleties that you have to deal with. So when H is equal to H prime, we have this thing blows up. So that's how these eigenstates look like. Okay. So this is analog of orthonormality that we had here. So in the finite or the discrete basis case, we had this condition. We only had, for every natural number n, we had a basis state phi n, and it followed this relation. But when it comes to continuous basis, for instance, the position basis, this is how the orthonormality comes in, the first line, like this equation, and this is how the identity comes in. So instead of the summation over n that we had here, right, here it will be integral because we need to sum over all continuous possible variables, ds. Okay, so this is analog of of the discrete case in the continuous case. Now, given this, we also know this identity, the delta function can be expressed in this form, which is a useful identity that we might need. Okay, now let's do the trick that we did earlier. Not here. Maybe make some space here. Right, so we know the state psi, right? We can apply identity operator on it, identity acting on psi. We just saw identity is this thing, right? So it's integral dx xx acting on psi. Okay. Now what is this? If I define this quantity, okay, that's what I've done below. Okay. Uh, Sorry, I'm repeating what I've already written down, so I'll just combine them. So the states, when I apply identity, this is an inner product, a complex number. I call this complex number as psi of x, right? Now I can write this as in this form. Now this is remember this is equivalent to writing a n phi n in the previous case, in the discrete case. In the continuous case, this is how you write the state. Now, when you talk about particle inner pods, harmonic oscillator, the wave function, which is a function of x, is basically this quantity, the coefficients. So if I had, let me go back to the example that we had. No, 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 no. Yeah. So if I tell you what x1, x2, x3 is, that's equivalent to specifying what the position of the particle is, right? Likewise, if I tell you what psi of x is, this quantity is for all x, that's equivalent to completely specifying the state. So you can think of this as a column vector with for each x there is a value psi of x. So it's a weird if I think of it as a vector, it's very complicated. That's why I don't usually do it. But this is how you should be. This is how it actually comes from. So if I tell you what psi of x is for all possible x, I can tell you what the exact quantum state psi is. Okay, they're equivalent way of describing the system. So this is if I chose position as a basis. Instead, if I chose momentum as a basis, so I'm looking at eigenvectors of momentum. So particles moving at a particular momentum, I'm calling them eigenstates. Now I can look at these are eigenstates of the momentum operator, whatever that is. Now using the above argument, I can momentum also like the eigenstates of momentum operator also forms a basis, and hence I can put identity here. Okay, I can again put identity here, and now I get this quantity. This is just like here, it's p psi. So this is okay, let me write. This is position representation of psi, and this is momentum representation of psi. So in both the cases, the state psi is same, but we are representing them in the position variable or momentum variable. It's two ways of representing the states. Okay. Now so if I write psi of x, which is this guy, in the position momentum basis, right? I can put an identity inside and do some. Okay. So what I did is I took this quantity and put an identity in the momentum basis inside in between, with which I can re-express the whole thing in this form. So psi of x is now related to psi of p, and the relation is given is controlled by this quantity, the overlap of x with p. Now, if I do the other way around, if I start from psi of p and do this, I'll get, inner product of xp will be replaced by ps. One thing you can notice is this looks like a Fourier transform. So if I put expectation of px to be this quantity, e to the power minus ipx by h cut, then psi of x and psi of p are related by Fourier transform. Okay, this is something that I mentioned last time. So psi of x is equal to integral dx e to the power ipx by h cut phi of p, and the other way around. Inverse Fourier transform will give me phi of p in terms of psi of x. So given a quantum state, I can either represent them in the position basis or momentum basis in terms of psi of x or phi of p. They're equivalent. They are related by a Fourier transform. That's what this means. Okay, now, so we said that in the position basis, where did we go? Yeah, this is how position operator acts on the states, eigenstates. And the momentum basis, this is how it acts. But we need to know how the momentum acts in the position basis and the other way around, right? We can't jump between, we can't do Fourier transform all the time we want to go compute, these two different quantities. So we need a consistent way of doing all of these in one single basis. So let's start from here. So we're looking at a wave function, psi of x, right? So we said it's a Fourier transform of phi of p. I've put h cut equal to 1 here for easiness of calculation. Now, and likewise, inverse Fourier transform will give me psi of p in terms of phi of x. It doesn't matter, but anyways. So yeah, so let's ask this question. Let's say I have this momentum operator p acting on psi, and how does this action look in the position basis? Okay, so momentum is acting on the state psi, whatever psi is, and I'm looking at it in the position basis. What I can do is I can put an identity, so integral of dp pp here, and then I just moved the integral dp to the side. When this p operator acts on this eigenstate p, it just pulls out the eigenvalue p and gives me the state back, right? So that's the p here, and I get the state back. So this inner product with this will give me this, and this thing inner product with this will give me this. Okay, these are complex numbers now. We know this guy is nothing but e to the power ipx by root 2 pi. Like they're related. I can substitute that. So this is how this expression looks like, and I can do a bit of math and see that if I take derivative, if I do this derivative, I'll get this quantity, right? When I do e to the power ip derivative of e to the power ipx with x, the ip would come down, which is exactly what I have here. So if I multiply by minus I here, then those two equations are equivalent. So these are just mathematical tricks. I'll send you the notes. If you have any doubts, you can ask me in the next lecture, next session. Okay. Now I just pull out the I. So the integral is over dp, right? So x doesn't have anything to do with it. They're independent. So I can pull out the dx outside. So what is left inside is basically the position representation of the state, right? So what we got is minus I. So see the action of p on the state side in the x basis is basically this. Hence, we can say in the position basis, momentum looks like this: minus I dou by dou x. So in in position representation, x acting on psi, x is just x cap, x times x, and p cap becomes minus I dou by dou x. Likewise, if I worked in momentum representation, one can show that, using the simple argument, but instead action of x on psi give in the position basis, the momentum basis, if you look, you'll see it will be given by I dou by dou P. So these are two ways in which I can work in. I can either work in the position basis or in the momentum basis, and correspondingly, the other operator would have some structure which I can figure out by this method. Is that okay? I'll stop for today. I'll stop here for today because it's already 7:15. I'll stop recording.